Mic check, mic check. Alright, something before I get started. The following is the summary or my understanding of the first read of the book, the 100-page machine learning book. Because I'm new to machine learning, I'm learning, and this is just my first read of this book. To be honest, there are so many terms that are new to me and I need time to get good at it. So, if you want to learn, if you're here to learn machine learning, you gotta get out of here. Because something I'm gonna say in the following session will be kinda not accurate or even completely wrong. This is the Jackson log. Let's go. The 100-page machine learning book. This is the first book, also the first learning material about machine learning. Right now I am at in the beginning of chapter 4. I finished 3 chapters and this is my first read. So I don't expect myself to understand 80% or 100% of the whole material. I only expect 20%. The 80-20 rule. This is the first read. It is impossible for me to understand everything because it takes several times of reading. For example, first time you get 5%, 20%. Second time when you read it, you get more because some of the terms you see it before. To be honest, it is not a easy read because there are so many new terms that I haven't heard of. It is a complete new topic to me, and I need to keep reminding myself, don't rush, be patient. This is the first time you learn. Don't be too harsh to yourself when you don't understand it. When you revisit this book, you will learn more. It's kind of like start small, be consistent, and have fun. Otherwise, I will burn out, lose my motivation, and this is the last thing I want. Machine learning. Let's talk about what I understand or what I have learned. I would rather say what I understand in the first read, in the first few chapters. Chapter 1 of this book is a general introduction. What is machine learning? Machine learning, in my understanding, like you have a bunch of data, you use that data to train a model or algorithm. I don't know what is an algorithm. I don't like fancy terms. I want to keep expanding this, keep break it down, keep deconstructing this fancy word into a smaller elements or smaller chunks that I understand. Maybe it's like a series of instruction or code or function, something like that. I don't know if it is correct, but what is machine learning? You have a bunch of data, you train a module, and that module is like estimator. After you train this model, you give a new input and the model can tell you what the output is. That's machine learning for me, in my understanding. I don't know if I'm correct, so let's move on to the next one. After the introduction of what machine learning is, then we have many types of machine learning, types of learning: supervised learning, unsupervised learning, semi-supervised, and reinforcement learning. Of course, there are more, but this book only focuses some of them. Number one, first one, supervised learning, probably the most common type of machine learning. Supervised learning would be like the data we have. For example, we have the data, we know the features, and at the same time we know the output. We define the output. So a data, we have a input and an output. With a bunch of them, train it with the model, and after you give a new data, the model analyzes the features of the new data, and then based on the training data, or what based on the training data, the model gives you the output. So supervised learning would be like this, would be like that. Unsupervised learning would be, now the data we have the features, but we don't have the label. So unlabeled data, we have a term. Instead of calling it data, we say example. One data, one example. Bunch of data, we call it data set. Is it? Forget it. Unsupervised learning would be, we have a bunch of unlabeled examples, and I don't know, we have some application in this kind of learning, like clustering, dimensionality reduction. Dimensionality reduction would be like a data, a input with many features. Each feature, we call it a dimension. For example, me, I'm 170 height and weight 65 kilogram. I'm a male. So now we have 3 data describing myself. So me, myself, as a single example, will have 3 features. Yes, 3 features: height, weight, and sex. So the dimension of the feature, we put all the data in a vector. Just think of it as a container to store the data. So it is a vector with the dimension of 3. 3 features, 3-dimensional feature vector. So in the unsupervised learning, sometimes we may not be interested in the output or the label. Sometimes what we want to do is to reduce the information, reduce the complexity. Reduce the from a, let's say, 3-dimensional vector to a 2-dimensional vector, something like this. So dimensionality reduction. Clustering, I don't know what it is. So let's jump into the next one. Semi-supervised learning. Semi-supervised, as the name suggests, part of the data, part of the examples are labeled and part of them are not. That's it. Next one. Reinforcement learning. I think this type of learning is not in the scope of this book, but the general idea of reinforcement learning, I think, would be, it is used for gaming or constant decision making. Like for gaming, after this step, you need to make the decision for the next step. That means it's kind of like a feedback loop. Like the input not only depends on the data, it also depends on the previous output. So this like two data sources. New data, and the decision you made in the previous iteration. So it's just a feedback loop. I don't know if this is correct. Who cares? I mean, it's just the first time I read this thing, and this is how I perceive it. If it is not correct, feel free to correct me. Leave a comment in the description, or maybe in the future I may find myself, man, you make a mistake in this video. It doesn't really matter, because as long as I keep learning, keep improving, boom, sweet. Next chapter. Chapter 2 would be math. To be honest, math is tough, way tougher than I expect. Although I'm studying mechanical engineering in year 1, I think year 1, year 2, I have attended some math class, so I've learned linear algebra, calculus, multivariable calculus, probability, and so I feel like I can handle it, but after reading a few pages, it is not the case. It's tough, but I try not to let the math to discourage myself. It's just it all comes down to fancy symbols. As long as you understand part of it, and then you keep expand your knowledge, keep learning, then you will get the big idea, get the big picture, and at that time you will think like, oh, this is not a big deal. It's all a matter of time. But because this is the first first pass of this book, again, I need to emphasize the objective of this iteration of reading. Of course I will read it a couple more times in the future, but this one, the objective is to understand or take a look of the big picture of machine learning. What elements are in there? Chapter 2, notation, definitions. We talk about what is a vector, scalar, some fancy symbols, matrix, functions, derivative, gradient, max, random variable. Probability is my weak point, so random variable, unbiased estimators. I have no idea what they're talking about. Bayes rule again, parameter estimation again, parameters and hyperparameters. Now I understand a little bit in this section. Parameters will be parameters controls, or a model is controlled by some parameters, and these parameters you can get it from the training data. For hyperparameters, we need to set it manually. Usually it's done by data analyst, data analyst. And that's the difference. One is the computer can do it, and the other one would be we need to do it. Classification and regression. Classification, we are giving a label to a example. It doesn't have to be binary classification, not black and white thing. Sometimes we have multi-class classification. For example, you input a sentence and you need the computer to tell you the part of speech of each word. For example, I eat chicken. Turns into noun, verb, noun. I don't know. My English sucks. But you get the idea. It turns your name. You give a input, some labels, or something like that. This is the classification. Regression would be giving you a value, a number. Oh, to be honest, I can't tell you the definition of classification and regression. I know classification, but what about regression? Gives you a value. For example, your data would be the stock market, the performance of the stock market. You train a model, and the model will tell you how good the stock is, how much it worth. Just give you a value. I don't know. Maybe it's a terrible example. Forget it. Model-based and instance-based learning. Model-based would be you have a training data. You use the training data to train a model. After you train the model, you can throw away the training data because what you need is the model. The model will tell you the output. However, for instance-based learning, instead of training a model, giving you extra stuff, or gives you the new stuff. Instance-based learning would be you use the whole training data as a whole to be the model. So use that training data as the model. For then, one of the learning algorithm would be K nearest neighbor, which I will talk about later. You take the input, compare to the training data, the training data that is closest to that input, and then based on the neighbors, the output of the neighbors, the computer will estimate the output for you. Instance-based learning. That means you cannot discard the training data, otherwise you will lose the whole model. That's instance-based learning. Shallow versus deep learning. Shallow would be, I think I've jotted down some notes, but it's not here. I can get it right here. It's far away from where I am here. Shallow would be a single layer. Deep learning would be more layers. I don't know, for example, just one layer would be a model. One layer. Input, data, and then one model takes the input, gives you the output. Single layer. Shallow learning. Deep learning would be stack of layers. Input, the first layer take the input, process it, give out the output, and this output would be the input of the next layer, and then keeps on and on and on. Deep learning until all the layers, you go through all the layers. Deep learning. I don't know, again, maybe I'm wrong. Next chapter would be the first mind-blowing, or just it drains my mental energy to understand this thing, which is the fundamental of algorithms. With linear regression, we have logistic regression, decision tree learning, support vector machine, K nearest neighbors. Of course, we have more, but these are the algorithm introduced in this book. So let me take a break. Then I'll finish this chapter. Now, coming back. First algorithm would be linear regression. We have a bunch of data, we plot it, visualize the data, and then what we need to do in linear regression is to come up with a solution a plane that catches as many data, as many examples as we can. So the plane itself is the solution. Then we input the data, and then the plane will map the output for you. Linear regression, a plane, linear, nothing bends. That's how far I can get. Beyond that would be some math. For example, the function of this plane is wx plus b. W is a vector. B is a scalar. Why it is defined like this? I don't know. I don't understand. That's it. That's it for linear regression. Of course, we have more, like in order to optimize this thing, we need to compute. Need to get a solution from a like we need to solve the objective function, and why it is defined in this way. I don't know. What is empirical risk? I don't know. Binary loss, overfitting. Overfitting, I know. Overfitting would be the model is straight. It is so perfect. You can say it catches every examples of every examples in the training data. Is so good or so well fitted to this training data that when you input a new data that is not very close to that training data, and the model just fail, just give you a wrong output. And this is the last thing we want. We want some flexibility, or we want it to think, to learn, not to replicate the training data. We want to have a what is that? The term would be generalization. We want to generalize. We want to, have some flexibility, and that's how far I can describe it. And then we have another term called gradient descent. No idea. Skip it. Next learning algorithm would be logistic regression. Logistic regression is not a regression, it's a classification. It's used for classification. There's a reason why it is called regression, but I think it's the math stuff. I don't know. Logistic regression would be classification. If we use linear regression, now it is very hard to describe without graphs or drawing. So I will try my best to describe it using words. Now if we use classification, let's talk about a basic binary classification. 0 or 1, A or B, black and white. If we use linear regression, let's say we want to use a plane to estimate the output. Sometimes the data set will. It is not a good idea to use linear regression, because if there is a example that's far away from a big group of data, then the computer will come up with a new solution, a new plane, that the plane takes care that example, but it will leave some of them behind. So it's like you can't have all. If you want to take A, you gotta sacrifice B. But B is also important in the training example, because a plane cannot bend. You can either tilt it, shift it. That's a big limitation. So logistic regression, it allows it bend. I don't know, it's a terrible way to describe, but now once the thing bends, we have a bigger flexibility. It fits better in a certain type of problem or data set. So logistic regression is something that bends. And then we have the solution. The whole solution is described using a formula, the standard logistic function, and again, math. So to optimize this thing, we need to maximize the likelihood, which I don't know what it is, and why it's defined in a certain way, I don't know. And then we need to we need to maximize the log value of the likelihood. And then after that will be some fancy terms that I don't know, I don't understand. Next one, decision tree learning. Decision tree learning would be... what is that? I don't know, decision tree learning would be a tree graph. You have a data and you want to set a what? I forget the keyword with a threshold and a feature. Maybe a feature with a bunch of data, and then we give a criteria to split the data so that we can have a answer. For example, we give a bunch of requirements to distill, to filter out some data. For example, we check a feature, whether the feature equals to 2.5, for example, just a random number for illustration. We check if that feature equals to a number, a thing. If it matches, then you go to the one path for the other check. Otherwise, you go to another path for other check. Split the data. And then we split it until we cannot split it, or the split is not meaningful. So what do you mean by that? The split is not meaningful. We have a term to define it. We call it entropy. Entropy. In thermodynamics, we have literally a term called entropy, and we have a whole topic for entropy. This is thermodynamics, but it doesn't apply to machine learning. It is a different way to think of it. Entropy, you can say it is randomness. For decision tree making, each split, we want to have minimum entropy, minimum randomness. That means if we try to split a data and it turns out all the data has the same label, like everything just comes to a side, then the entropy will be 0 because everything will be the same. No randomness. However, if we want to split it, it turns out it's 50-50. Then the entropy is maximized because you don't do anything to separate this thing. You separate a thing and it turns into a complete 50-50. We want a definite solution. We want the answer. We want to know the outcome. We don't want to make things, you want to keep. We want to increase the resolution. Keep increasing the resolution. We want a clear picture. We want a definite. Give me a word. Give me a label. Give me the solution. Not a Because if you split it into 50-50, basically you do nothing. You help nothing to solve the problem. And that is when the decision making, the decision tree ends. We can't split anymore. So that's how we define entropy. And of course we have math to do it. I don't know, I don't understand the math. Now next one, support vector machine is for classification. If linear regression gives you a plane to catch all the training data, support vector machine would be, it gives you a plane to separate two sets of labels, or two sets of data with different labels. We should split it, not catch it, split it. Support vector machine. That's the way it's defined. If you visualize the data, or you plot it, and it turns out you cannot separate the data using a plane with a plane, then we need to do some tricks to visualize the data in a higher dimension. For example, if you plot the data in a regular 2D XY plane, XY graph, and you cannot use a plane to slice it, then step again up, visualize in a 3D, then hopefully we can see the pattern, but it is not guaranteed, so you gotta try it. And we have many ways to visualize in a higher dimension. We have a term called kernel trick, and the details of kernel trick is crazy. I don't know what it is. It's math, it's terms, it's things that I don't understand, not because I cannot read English, but it is the term that can help me understand the thing. Next one, k-nearest labels. I just talk about it. It is not controlled by the parameters. We don't have parameters in this label. It uses the whole the training data as a whole to help you solve the problem. It compares. We take the input, compares the closest neighbors, and see, compare it, and then based on the neighbors, I give you the output. Of course, we have math to do it. Skip it because I don't understand. So that's the end of chapter 3. I take half an hour to summarize what I've learned or what I understand in the very first few chapters. Now it is tough, so I'm gonna keep doing it. I only have a few more chapters, and after that I will make another video to summarize what I understand. That's it. Time's out, and I'm gonna eat something. See you soon.